The concept that we will now talk about is that of energy of a system. You probably have already seen this concept in other contexts, such as dynamics. Here, we will use the energy concept as follows. As the energy of a system vanishes, the system will stabilize. As the energy of the system increases, the system gets more unstable. We will now discuss some concepts of energy on specific examples. To begin with, I will talk about the classical pendulum system that will change us from the usual mass spring system. The pendulum has mass m concentrated at the tip of a rod of length L. It is subject to gravity, and its degree of freedom is called theta. The equation of motion of this system is ml squared theta double dot is equal to minus mgl times sine theta. We simplify the expression, crossing out all the redundant terms to obtain theta double dot plus g over L times sine theta is equal to 0. Let us now introduce two elements: potential energy and kinetic energy. In this particular context, the potential energy is measured as the potential energy of the mass m as it stands above its rest position, which is about here, in such a way that as the pendulum swings, it actually goes through this rest position. The potential energy is best computed as the distance separating these two levels, the level at which m stands and the level at which the rest position stands. And that is given by L times 1 minus cosine theta. The corresponding potential energy will be m g L times 1 minus cosine theta. The kinetic energy is simply the speed at which m travels. So it is 1/2 of m v squared, where v is the speed of the pendulum. Now, v is equal to theta dot times L. And therefore, the kinetic energy will be 1/2 of m L squared theta dot squared. The total energy of the system is the sum of the kinetic energy and the potential energy, which is equal to mg L times 1 minus cosine theta plus 1/2 of m L squared theta dot squared. We can see that as the pendulum swings around, we have no losses. Okay, there is no drag, no whatever. Therefore, we should have that the energy E is constant. Let us prove this by taking the derivative of E. dE dt is equal by definition of mg L sine theta theta dot plus m L squared theta dot theta double dot, which is equal to theta dot times theta double dot plus g over L times sine theta. And of course, this quantity here is equal to 0, which indeed proves that the energy is constant. In some way, there is enormous value to knowing this. Indeed, what it means is that the system never stops oscillating, and we know how much energy is being stored and kept there. We can use this kind of information to obtain very useful information about, for example, the shape of the trajectories of the pendulum. Now, what do I mean by this? I mean the following. If I erase this point, what I could do is write what does the expression E is equal to some value A look like. Well, if E is equal to 0, then from this we see that this term must be equal to 0 and that term must be equal to 0. That is, in the theta dot plane, our system is bound to stay just about here. Okay? Just at 0. Now, if E is just a little bit greater than 0, say some epsilon, then we are interested in plotting what the level set of E looks like. This is less trivial. However, once again, we can borrow the idea of linearization to say that cosine theta in the vicinity of 0 is about equal to 1 minus theta squared over 2. So, for the purpose of illustrating what happens, I'm going to erase that 1 minus cosine theta and replace it by theta squared over 2. Now we have theta squared over 2 times a constant term here. We have theta dot squared times a constant term. Must be equal to some number epsilon greater than 0. This is the equation of an ellipse. In theta dot. And so it looks pretty much like this. What that means is that up to numerical details where we choose the exact size of the ellipse by finding what the exact values of this guy and this guy are, we can tell that in the theta dot plane, the trajectory will be somewhere on this ellipse. Now we can study more details about where it's going to go. For example, wherever theta dot is positive, theta must increase. Wherever theta dot is negative, theta must decrease. So we can immediately say that whatever trajectory happens on this ellipse, it must be something like that. And we see that will result in a trajectory which is an ellipse in the theta dot plane, or if we project it on theta, it is like an oscillation on theta and another oscillation on theta dot, which is consistent with what we know about the system. Now, the great value this concept is that it applies not only for simple systems such as this pendulum system, but much more complicated system as well. Before I go to more general experiences on how to compute the energy for larger systems, I want to talk a little bit on the fact and the relationship that exists between energy and stability. The energy we will work with now will be, for a change, that of a mass spring system with a dashpot. The mass spring system with the dashpot is shown to be something like this, where the mass is attached to a wall and a dashpot is added to the system. The mass is M, the spring has stiffness K, and the dashpot has viscosity coefficient mu, in such a way that the equations of motion reads, if I call x the position of the system, and if I take and compute x from the position at rest for this system, the equations of motion look like m x double dot plus mu times x dot plus k times x is equal to 0. Now let's talk about energy. And let's see how the energy relates to the fact that the system dissipates and eventually stops thanks to the shock absorber. When we take energy concepts, we again talk about the kinetic energy, and the kinetic energy is 1/2 of m x dot squared. The potential energy is what is stored in the engine, the spring, sorry, as is by definition 1/2 of k x squared. The total energy is 1/2 of m x dot squared plus 1/2 of k x squared. Notice that in the x dot plane, the ISO values, the ISO level curves corresponding to this level of energy will look like and will look exactly like an ellipse. For non-zero energy, the ellipse is like this. For zero energy, the ellipse will be like that. Again, this is x dot. Now, do the trajectories stay on the ellipse as they did in the previous example? The answer is no. Indeed, if we compute d dt of E, the energy, we get first to compute the time derivative of this guy, which is m x dot x double dot. We then get to compute the derivative of this guy, which is plus k x x dot. Therefore equal to x dot times m x double dot plus kx. Now, using the equation of motion, mx double dot plus mu x dot plus kx is equal to 0, I can replace mx double dot plus kx by its value as a function of mu x dot, and we obtain that the derivative of E is equal to minus mu x dot squared. What that means is that the derivative of the energy is negative, sometimes 0 whenever x dot is equal to 0, but otherwise negative. It means that as soon as the mass moves, the dashpot uses energy. And so, the trajectories look more like what follows. Starting from a given point, say x dot is non-zero, the system will slowly die off, possibly going through a couple of oscillations, but eventually die off. This is therefore a very important notion that we can link the fact that energy decreases to the fact that the system is cooling down, stabilizing towards 0. Okay? That is a fundamental element of system dynamics. Now, too bad we will not have time to read about it further. However, all I can say is that it is closely linked to Lyapunov stability theory. I will not go any further on this topic. However, those of you who are eventually interested in knowing more and taking controls classes at the advanced undergraduate or graduate level will necessarily see that concept come back sooner or later. Now, we can close this discussion by saying what the energy looks like in general systems. Well, in general systems, you may have a variety of elements. Some are like this, some have masses, you may have dashpots, Okay, you may have like weird combinations of masses and dashpots organized and attached to a particular wall. You may have a pendulum swinging under the mass, okay, etc., etc., etc. The energy of the system, okay, will be the sum of the kinetic energies and the potential energies. Right? Now, the computation of these kinetic and potential energies is specific to the mechanical system which is at hand. And so I will not pursue this matter any further. I would like, however, to go back to the notion of stability and instability by considering another example. This is a simple example. Let's take the slope and let's say the slope is at about 45 degrees to make matters simple. And we have a mass m free to slide down the slope. Okay? And let's say that for the sake of the example, we have no friction. We know that then the energy must be constant. Let's look at what that means in the case of this particular example. Let h be the height of the mass above a reference altitude, which would be 0. Up to a constant, the potential energy is m h g. We assume there is gravity. The kinetic energy is 1/2 of mv squared, where v is the speed of the particle. Okay? Now, let's compute the equations of motion for this guy. M, what will it look like? Well, we can say that the energy E is equal to 0. You remember, this is the 1 degree of freedom equation of motion that we can obtain from this. Let's write this. Okay, E is equal to mhg, which is also mg times minus x times square root 2 over 2. Where x is counted to be 0 here and counted positively this way. Plus 1/2 of mv squared, which is 1/2 of m x dot squared. Therefore, dE dt, which must be equal to 0, is equal to minus mg x dot times square root 2 over 2 plus m x dot x double dot. Simplifying things a little bit, we cross the m, we cross the x dot, and we obtain the equations of motion. X double dot is equal to m g square root 2 over 2. No deep miracle here. However, and we know, by the way, that this is a constantly accelerating motion. But we can see it also from E. What does E show? E is constant. Okay? So we need to plot the curves, the level curves of E, and we know that for a given level of E, x and x dot will be riding the corresponding level curve. So let me erase this. And go back here. To say that the level sets look like square root 2 over 2 times m g x is equal to 1/2 of m x dot squared. Cross the m, cross the 2's, and I find that x is equal to 1 over g times x dot squared. That is the equation of a parabola. If I write it as a function of x dot, so in the plane x dot, this parabola for a given value of g will look like something like this. And you see what happens. Suppose that my original speed and original position are here. Then we go this way. Oh, by the way, this is the level curve corresponding to E is equal to 0. My mistake. So if we take a point here, we see that the only thing you can do, because x dot is positive, is to increase x, which makes x dot increase, which makes x increase. And you see that pretty quickly x escapes. Now, if the initial position and the initial velocity are here, then the system escapes, but the other way, towards negative value of x dot, and still positive values of x. What does this mean? Well, it means it doesn't quite do that. Instead, what it does is, since the velocity is negative, x decreases. And therefore the system goes up here, okay, and then moves on to escape that way. So we have this complete picture of the behavior of the system summarized by this level set of the energy. Now the energy may not be equal to 0, but instead might be equal to a positive number. If there is a positive number, that means that this equation needs to be modified to include the value E, whatever it is here. Okay? And so what we obtain is that x is equal to the same quantity as before, minus E over G. And what this means is that the value of x, when x dot is equal to 0, instead of being at 0, is a little behind. And that the resulting level curve is otherwise the same parabola as before. It is just shifted, and the same behaviors ensue. When the energy is negative, I believe you understand the picture, and yes, what you have is a level curve which is now shifted to the right. In all cases, however, the system first goes to 0 speed, then takes some speed and goes to infinity, which is the equivalent of saying the mass goes up, stops, and goes back down, and then goes towards infinity. This is a sure sign of instability. And as you see, part of it is because the level curves of the energy are open, unlike what we have seen before, where the same level curves were closed. Thank you.